Okay, in this example, I'm going to do a one-way between subjects analysis of variance using hand computations. So let's pretend we have three groups. A group of people who are assigned to watch a depression commercial, a group of people who are assigned to watch an anxiety commercial, and a group of people who are assigned to watch a control group commercial. That'll be our independent variable commercial type with three levels, and our dependent variable here we'll say is, let's say, depression scores in this hypothetical example. So our null hypothesis is going to be something like the means for each group in the population are equal, and our alternative hypothesis is going to be that there is at least one difference between the means. At least one, right? So we're going to compute the ANOVA by hand using, first we'll want to set up what's called an ANOVA table so that we can partition the variance into effect and error variance, or between and within variance. So we'll set up a table like this that has a column for the source, a column for the sum of squares, a column for the degrees of freedom, a column for mean squared variance, and a column for the F ratio, and a row for between or effect, a row for within, and we can create a row for total. Right, so first thing we'll want to compute are the sum of squares for between and within. Now this is where we partition the total sum of squares into the parts that make it up, which are the between and within sum of squares. So we'll use a computational formula for that to save a little bit of time. The computational formula for sum of squares between to get that, we'll need the sum of x for group 1 squared over the sample size for group 1 plus the sum of x for group 2 squared over the sample size for group 2, and then the sum of x for group 3 squared over the sample size for group 3. There's only 3 groups here, but we'd keep going if there were more groups. And then finally we'll subtract the sum of all the scores squared over the total sample size. Alright, so here first we'll need to add up all the scores in each group or each condition. So first we'll get sum of x 1, and that will add up to 85. And we'll get sum of x for group 2, which adds up to 55. And then sum of x for group 3, which adds up to 33. Right, so now we're able to plug into the equation for sum of squares between. We'll take 85 squared over 7 plus 55 squared over 7 plus 33 squared over 7, and then finally we'll subtract the total which is 173 squared over 21. So working through this, 85 squared divided by 7 gives us 1032.1429. Roughly. And then we add 55 squared over 7, which gives us 432.1429. And we add 33 squared over 7, which gives us 155.5714. And then after taking the sum of all those values, we'll take 173 squared divided by 21, which is 1425.1905. Okay, so now we just add and then subtract, and we'll have our sum of squares between. And I get 194.6667 as our sum of squares between. So we can put that into our table for our ANOVA table. What was that? 194.6667. So now we can get our sum of squares within. So sum of squares within is taking the sum of all the squared scores. So this is a bit of a pain because we have to square up all the scores and add them together. And we subtract basically what we computed up here on the right hand side. So this will come down over here. So we got for that 1619.8572, adding these three numbers together. .8572. Alright, so we need to square all the scores and add them up. So many calculators will have a shortcut for doing this, but in case yours doesn't, you just simply square very carefully 81, 100, and so on. Square all of the scores, and then add them all up. So if we take all of these squared scores and then slowly add them all together, we should get 1,677. So to get SS within, we have 1,677 minus 1,619.8572, which gives us 57.1428. So we have our sum of squares within, 57.1428. So that's basically the hard part is over. Degrees of freedom between is the number of groups minus 1. So that'll be 3 groups minus 1. So we'll have 2 as our degrees of freedom between. Degrees of freedom within is total sample size, which here is 21, minus k, which is the number of groups. So our degrees of freedom here are 18. Right, we can get the total sum of squares, assuming we've calculated the between and within correctly. We can get the total by adding our between and within sum of squares together. I get 251.8095. Alright, so now to get the mean squared variance for, or the mean variance for between or effect, we would take 194.667, which is our sum of squares between, and divide it by 2, which is our degrees of freedom between, get 97.33. And we do the same for our mean square error variance. We take 57.1428, which is sum of squares within, and divide it by 18, which is degrees of freedom within, and we get 3.1746. And we divide our mean square effect, or between, by our error, and we get a very large F ratio of 30.66. So that is without a doubt a statistically significant value, because this basically says our effect variance is 30 times greater than our error variance. However, just for the sake of going through the motions of what we would do if we needed to look this up, we could put in our degrees of freedom numerator, which is 2, our degrees of freedom, or look up our degrees of freedom denominator, which is 18, enter our alpha, and get our F critical value that we would need to get to is 3.55. So these are generally tabulated in tables of F ratios where you can look up what would the F critical value be for a given alpha. So we would need to get 3.55. Clearly we've surpassed that by quite a lot. So this the p-value that corresponds to this is going to be extremely low. We could look it up to an 18 degrees of freedom and 30.66 as our F, and it's basically 5 zeros 0.00001 is our p-value. So clearly that's well below any alpha value we might use to determine statistical significance. We could also compute, at this point, we know that there is at least one difference between the means for these groups, but we could also compute the effect size. The one effect size that's commonly reported for ANOVA is eta squared, and that's interpreted basically as the proportion of the variance in the dependent variable, or the proportion of the total variance that's accounted for by the effect, or by the between sum of squares. So to calculate that, we simply take 194.6667, which is our between sum of squares, and divide it by the total sum of squares, which is 251.8095. And we get a very large 77% of the variance in depression scores is accounted for by which commercial the participant watched. Alright, and next step would be if we might want to determine which pairwise differences are significant. There's various ways to do that. One popular way is to do a Tukey test to determine which of these pairwise differences are in fact significant. So in order to do the Tukey test, we'll of course need to get the means for each group. So let's go ahead and compute the means for each group. So the depression group would be 85 divided by 7 gives us 12.1429. So our mean for the depression group, 12.1429. Our mean for the anxiety condition is 55 divided by 7 gives us 7.8571. And finally, for the control group, we get 4.7143. So the largest difference, which is very likely to be statistically significant with the Tukey test, is going to be between the depression group and the control group. I'll start with the largest difference, and then I'll go to the next largest difference, and then we'll do all pairwise comparisons. So first, to do the Tukey test, we need to write down the formula. The formula is based on the studentized range statistic, which is usually symbolized by Q. We're basically comparing two means. So first we're going to compare group 1 to group 3, and then divide it by the standard error, which will be MS within. It's MS within, which we calculated earlier, divided by n, and the square root of that. So here we have 12.1429, subtract 4.7143. I mean 4.7143. Divided by the square root of our MS within, which we calculated earlier in the F table, in the ANOVA table rather. MS within is 3.1746. Divided by our sample size, which here is 7. So we take 12.1429, subtract 4.7143, we get 7.4286 over 3.1746 divided by 7. We take the square root, we get 0.6734. So if we take 7.4286 and divide it by 0.6734, we get a Q value of 11.03, which is certainly going to be statistically significant at any alpha. But we'll go ahead and look up in a studentized range statistic table with alpha 0.05, we have 18 degrees of freedom. 18 degrees of freedom in the numerator, and we are comparing 3 means, which is the first column. So we need to get to 3.609 in order to reject the null hypothesis for each pairwise comparison. So our Q critical is 3.609. This is well above that. So we'll go ahead and now compare groups 1. Let's go ahead and compare groups 1 and 2 using the same formula. So group 1 has a mean of 12.1429. Group 2 has a mean of 7.8571. And we're going to divide that by the same denominator, the same error term we used before, which is 0.6734. We take 12.1429, subtract 7.8571, and divide it by 0.6734, and we get a Q value of 6.36, which is also well above our Q critical value, so we'll consider this difference to also be statistically significant. So we now know that our depression group, commercial group, has significantly higher depression scores than our control group. Our depression commercial group has significantly higher depression scores than our anxiety group. And now finally we can do the last comparison, which would compare our anxiety group to our control group, and it will still have the same error term. So we have 7.8571 subtract the mean for the control group, which is 4.7143, over our error term, 4.66, which is also above our Q critical value of 3.609. So we can conclude here that the anxiety commercial group had significantly higher depression scores than the group assigned to view the control commercials. So in this case, all pairwise differences were statistically significant. So that was our example of conducting a one-way between subjects ANOVA by hand, and then also doing the Tukey test to follow up the one-way between subjects analysis of variance.